Great, Honors Chemistry. This is lesson 11 on Avogadro's number. So we're going to learn about what a mole is and why it's used, and how it allows us to do actual chemistry in a lab as opposed to just on paper. The first part of the assignment is really a bit of a review that we did in class. If you didn't get it done in class, you can do it at home. And what you would do is go to this website. So there's a live link both in the Canvas site under lesson 11 and on this sheet in the Canvas site. Either place, you click on it, it will take you to a site called Colorado PhET, and what they have is a lot of science simulations for various sciences. And what I want you to do is go to the one that this link will lead you to, which is balancing chemical equations. And when you get in there, there will be two things you can click on. One of them says game, so you click on game, and that will pull up three levels: level 1, level 2, and level 3. And what I'd like you to do is click on level 1, and it will give you a chemical equation, and you should write that equation down here. And then I want you to balance that equation. And then once you've done that, go back into PhET and put in whatever your answer is, whatever the coefficients are in that balanced equation, into PhET and see if it tells you that's the right answer. Do that for two level 1 equations, and then level 2, do it for two level 2 equations. Those are just a little bit harder. So again, each time it gives you an equation, you come over here, and I've given you 5 spaces on the paper here. Just write the equation 1, 2, 3, 4, 5. So it's a total of 5 equations. Just write the equation down, balance it the way you learned in lesson 10, and then go back to PhET and check it out and see whether you got it right. Then I want you to do one level 3. That's the more difficult ones. Go ahead and do one of those, but you can still balance them using the methods that we learned. And then go back into PhET and see if you got the correct answer. So it's about 10-15 minutes to do this. Okay, and if you didn't get it in class, if you got it done in class, you're done. If you didn't get it done in class, you can go ahead and do this at home. All right, now we're going to go on to the assignment for this. So you should have watched the video on lesson 11. And so I've asked you just some general questions here. I'm going to go ahead and speak them to you. I'm not going to write them because I don't want you to just copy. I want you to be able to explain in your own words based on the lesson, the video, and based on what I'm saying here. Okay, so what is Avogadro's number? Avogadro's number, this I will write down, is this number, (10 to the 23rd) of anything. It's simply a number of things. So just like a dozen means 12, it could be 12 donuts, 12 eggs, 12 pizzas, whatever you have 12 of, it's called a dozen. So Avogadro's number is simply this number. And usually it's used in reference to atoms and molecules, numbers of atoms and molecules. It's a really big number of atoms and molecules that we can use, so that if we use a very large number, we can actually work with them in a laboratory. It's enough that we can actually see them and weigh them on a scale. We can't weigh a single atom or a single molecule. So this gives us a big basket of atoms or molecules to work with, so we can work with them in a lab. The question is, why this number? Why did they pick this number? And that's discussed in the instruction video. Okay, I'm not asking you that question here, but you should understand, why did they choose this number? Okay, what is a mole? A mole is actually the word we use in class or in chemistry, not just in class, in chemistry, meaning the same thing. You never hear the term Avogadro's number. I mean, you hear it, but when you use it in actual chemistry practice and doing labs and doing assignments, you're going to call it a mole. And it actually has the abbreviation MOL. They decided to take the E off it for some reason and just call it mole. So this is mole. Okay, what is atomic mass? Atomic mass is the average mass, this goes back several lessons, of all of the isotopes of a particular element. It's the average of all the isotopes, of the masses of all the isotopes of a particular element. And that's the number below each element on the periodic table that has a decimal to it, because when you take an average of all the isotopes, you're likely going to come up with a decimal number. Mass number is the mass of a specific isotope. So carbon-12 is a carbon atom that has 6 protons and 6 neutrons. That's a total of 12. Carbon-13 is a carbon atom that has 6 protons and 7 neutrons, so that's 13. And then if you take all the different isotopes of carbon and you average their masses, you'll get the atomic mass. So the mass number is the mass of a specific isotope. What is molar mass? So molar mass is the mass of a mole of atoms or molecules. So for carbon, for example, the atomic mass for a carbon atom is 12.01. You can get that off your periodic table. But if you have a mole of carbon atoms, then that will be the molar mass. And it happens that, and this is why this is a magic number, it happens that that will also be 12.01, the molar mass, the mass of 1 mole of carbon atoms. The difference is the unit of measure is grams. For atomic mass, it's atomic mass units. It's basically a measure that's too small for us to be able to measure, to actually be able to put on a scale. There's no scale that can measure atomic mass units. However, there are scales that can measure grams, and so what it does is the molar mass converts the number of atomic mass units to the same number but in grams. So 12.01 atomic mass units is the atomic mass of carbon. 12.01 grams is the molar mass of carbon. That is the mass of 1 mole, this number of carbon atoms. And that's why this number is so significant, because the number is the same, 12.01 and 12.01. Stoichiometry. So stoichiometry is basically the math of using a chemical reaction. It's how do you figure out if you put in so many grams of methane, how many grams of water are you going to get out of that chemical reaction? So it's the mathematics that involves using and manipulating chemical reactions. And we'll talk more about that. That's what this unit is largely about. Okay, so the first thing we're going to do is we're going to compute some atomic and molar masses. And so here's an example how to do it. So the example is, I didn't write it here, but it's for water, H2O. So you have hydrogen, you have 2 hydrogens, so 2 atoms of hydrogen. For oxygen, you have 1 atom of oxygen. And then what that produces is 1 water molecule. Okay, so 2 atoms of hydrogen plus 1 atom of oxygen gives you 1 molecule of water. Now if you come over here, you have the 2 atoms of hydrogen, and there's the mass. Now it really should be 1.01. When I teach regular chem, sometimes I round it to a whole number, so I'm going to scratch that out. So it's 2 times 1.01, and that's going to be 2.02. So that's the mass of the hydrogen that's in a water molecule. For the oxygen, it's going to be 16.0, so I'm going to change that. There's 1 oxygen atom, and we're going to call it 16.0. So that is, it is 16, but it's 16.00. We're going to 2 decimal places. And when you add these 2 together, you get 18.02. Okay, instead of 18, and it's in atomic mass units. So that's the mass of a single water molecule. Okay, so what we're asking you to do here is just for these 4 different compounds is compute the atomic mass and then the molar mass of each of these. So I'm going to do these 3, carbon dioxide, peppermint, and acetic acid, which is basically vinegar. And then you'll do the 4th one, vanilla. But you should do all of them actually, but just watch my answer to see if you did them right, okay? Okay, so you need to get out a periodic table. So to figure the atomic mass of carbon dioxide, we come over here. First of all, we write down carbon. And how many do we have? We have 1 atom of carbon, so I'm going to put a 1 there. And then oxygen, we have 2 atoms of oxygen in this. Now we have to multiply that by their atomic mass. So for carbon, it's 12.01. And for oxygen, it's 16.00. And you multiply that out, you get 12.01. And 2 times 16 is 32.00. And when you add these, you end up with 44.01 atomic mass units. That's the mass of a single carbon dioxide molecule. Now, if you have a mole of these, that is times 6.01 6.022 times 10 to the 23rd, what's the mass of that, of a mole? And the answer is, and this is why they use this number, is you get exactly the same number. 44.01, except it's in grams, which is the standard unit of measure for chemistry all over the world. We have scales in the classroom that measure in grams. So you can actually think of this in a different way. If I weighed carbon dioxide on a scale, took the mass of it and found that I had 44.01 grams of carbon dioxide, then that would tell me exactly how many molecules of carbon dioxide I have. I have a mole, and that would be 6.022 times 10 to the 23rd molecules. So it actually gives us a way of counting this vast, this humongous number of molecules by just knowing what their mass is. So you can work backwards from mass to the number of molecules, which we couldn't possibly count if we just tried to count them one by one. So these are the answers that I'm looking for. Atomic mass is 44.01 AMU. Molar mass is 44.01 grams. Okay, let's go over to peppermint. So you have C, H, and O. There are 10 of the carbon, 20 of the hydrogen, and 1 of the oxygen. For carbon, again, go to the periodic table right there, 12.01. And that's going to equal 120.10. For the hydrogen, it's 20 times 1.01, and that's going to equal 20.20. And for oxygen, it's going to be times 16.00, and that's going to equal 16. Okay. And when you add this up, okay, and that gives us 156.30 atomic mass units for a single molecule of peppermint. If you multiply that by 6.022 times 10 to the 23rd molecules of peppermint, then you get 156.30 grams. Small g is the abbreviation for grams. So atomic mass is this, molar mass is the same number, different unit of measure. That will only happen if you multiply by this number. That's why this is the magic number, to get that to convert. Okay, let's do acetic acid. You have carbon, hydrogen, oxygen. Okay, so you have 2 carbon, 4 hydrogen, 2 oxygen. The carbon, we've done this a few times, is 12.01. Hydrogen is 1.01. And oxygen is 16. So this is going to be 24.02. This is going to be 4.04. And this is going to be 32. Okay. And if we add them up, we get 6, 0.0, and 6. 60.06 AMU, that's for a single acetic acid molecule. And if you multiply that by a mole, that's going to equal 60.06 grams. Is how much a mole of these would weigh. So atomic mass, molar mass. Okay, I'll leave vanilla for you to do. You can figure out how much a vanilla molecule weighs, or a mole of vanilla molecules weighs. Okay, and I'll leave that one for you to do. Done exactly the same way. All right. Now what we're going to do is we're going to learn how to kind of scale a molecule and how much of each element you need to build that molecule, both in terms of numbers of moles and numbers of grams. Okay, so I'm going to have you fill out these tables for each of about 4 different elements. This one's already filled out for you, so let me explain what you do. We're talking about carbon dioxide. So what you need is, in order to make carbon dioxide, you need carbon, oxygen, and then the bottom line represents the combined carbon dioxide. Those combined into carbon dioxide, CO2. So the second column is the number of atoms or molecules. So you need 1 carbon in carbon dioxide. There it is, 1C. You need 2 oxygen in carbon dioxide. So there that is O2. When you put those two together, you get one carbon dioxide molecule. Don't add these numbers. It's like when you make a bicycle, you need one seat and two wheels to make one bicycle, not to make three bicycles. So that's the number of carbon dioxide molecules when you put all this together. Okay, now we go to the periodic table, and we've seen this number already a few times, 12.01. So it's 1 times 12.01 equals 12.01 AMU for the carbon atom that's in carbon dioxide. For the oxygen, you have two of them. And the mass from the periodic table is 16, so 2 times 16 is 32 atomic mass units. So the total mass, the total weight for the carbon dioxide is adding these numbers. 12.01 plus 32 will give you 44.01 atomic mass units for a single carbon dioxide molecule. Now, we've talked about a mole. A mole is this magic number right here. Now, they could have picked any number to be a mole. So why did they pick this number? They could have picked any number. They could have picked a nice round number like 1 times 10 to the 20th power, which would be a 1 with 20 zeros behind it. Why didn't they pick that? That's a nice round number. Why this weird 6.022 number? Because whatever you call a mole, if you take the number of atoms and you multiply it by whatever you decided to call a mole, you're going to have 1 mole. So one carbon atom times a mole is 1 mole of carbon. 2 oxygen atoms times a mole is, each times a mole is 2 moles of oxygen. 1 carbon dioxide molecule times a mole is 1 mole of carbon dioxide. And that would have been true whatever number you chose for a mole. What wouldn't have been true, and what this number is uniquely provides for us, is this. That if you have an atomic mass of a single carbon atom of 12.01 and you multiply it by this number and this number only, it will give you the exact same number right here, but in grams. So 12.01, 12.01. No other number would do that. 1 times 10 to the 20th times this would give you some weird number over here. It wouldn't be 12.01. If you take 32 and multiply it by this number of oxygen atoms, you end up with 32 grams of oxygen atoms. That's a mole of oxygen atoms. And finally, if you take this mass of carbon dioxide molecules, you multiply it by this number, you'll end up with the exact same number, but in grams of carbon dioxide in a mole of carbon dioxide. So that's why this is a special number. It has to be this number, so you end up with the same number of grams. So you notice that the atoms and the atomic mass 1, 2, 1, and then these numbers are exactly the same as these numbers. The only difference is here you're talking about moles, and here you're talking about grams instead of atomic mass units. So what that means is eventually when we get to a little further along in this concept, you can skip doing this. Okay, this is just trying to show you initially how a number of atoms and molecules converts into numbers of moles. But we're really interested in working in moles. That's why they have a mole. It's a big number, big enough for us to be able to see it and weigh it. And so we're really interested in working in moles, not in atoms and molecules. Now over here in the far column, and this wasn't in the instruction video on this lesson, but it's just asking the number of atoms or molecules. So if you have 1 mole of carbon, then you're going to have 6.022 times 10 to the 23rd carbon atoms. If you have 2 moles of oxygen, you're going to have 2 times 6.022 times 10 to the 23rd, or this number right here, atoms of oxygen. And if you have a 1 mole of CO2, then you have 6.022 times 10 to the 23rd molecules of carbon dioxide. Okay, so now what we're going to do is we're going to come down here and we're going to answer questions based on this. And what you're really interested in is what's in this red box here. That's why it's drawn around. So everything in here is referenced to 1 mole of carbon dioxide. So in order to make 1 mole of carbon dioxide, you need 2 moles of oxygen. To make 1 mole of carbon dioxide, you need 1 mole of carbon. To make 1 mole of carbon dioxide, you need 12.01 grams of carbon. 1 mole of carbon dioxide, you need 32 grams of oxygen. And if you have 1 mole of carbon dioxide, then that will weigh 44.01 grams. Similarly, we can talk about molecules. If you have 1 mole of carbon dioxide, it's going to require a mole of carbon atoms. A mole of carbon dioxide is going to require 2 moles of oxygen atoms. And 1 mole of carbon dioxide will provide you with 1 mole of carbon dioxide molecules. Now, so what if I wanted 2 moles instead of 1? Then I would need to double any of these. Okay, if I wanted 2 moles instead of 1, I'd need to double these. If I wanted 3 moles instead of 1, I'd have to triple these, multiply any of these by 3. It's like if you're given a recipe for a cake and it tells you you need 3 eggs and a pound of flour and 2 cups of sugar, and you want 3 cakes instead, then you need to triple all of those ingredients to make 3 cakes. It's just like cooking. So you just scale things depending on how many moles of carbon dioxide you're talking about. So let's go ahead and I'll show you how I'd like you to write out these answers as well. So how many CO2 molecules in 1 mole of CO2? So here's 1 mole of CO2, and this is how many CO2 molecules right there. So you can just simply write complete sentences, please. Okay, so there are 6.022 times 10 to the 23rd molecules of CO2 in 1 mole of CO2. Whenever you write a number or a compound, anything in stoichiometry and chemistry, it's always units of measure and the substance. Unfortunately, there's no abbreviation for molecules, but the good news is you really don't use that very much. Right here is a unit of measure, moles, and the compound, okay, the substance. So it's always units of measure and a substance. All right, let's go on. How many grams is 1 mole of CO2? So 1 mole of CO2, everything here is referenced to 1 mole, and there's the number of grams. It's 44.01. So you can write, there are 44.1 grams of CO2 right there in 1 mole of CO2. Again, unit of measure is grams, substance is CO2. Unit of measure here is moles, substance is CO2. Always have both of those things after any number in chemistry here. Okay. So number 3 is how many moles of oxygen in 1 mole of CO2? So in 1 mole of CO2, you need 2 moles of oxygen. You need twice as many oxygen atoms as you have CO2 molecules. So it's a 2 to 1. There's 2 oxygen, in other words, for every 1 CO2 molecule. So the question is how many moles of oxygen in 1 mole of CO2? So there are 2 moles of oxygen in 1 mole of CO2. Again, unit of measure and substance. Unit of measure and substance. Number 4, how many grams of oxygen in 1 mole of CO2? So again, you come over here, everything here is reference to making 1 mole of CO2. So how many grams of oxygen? It would be 32. 32 grams of oxygen are needed to make 1 mole of CO2. There are 32 grams of oxygen in 1 mole of CO2. Next question. How many carbon atoms in 1 mole of CO2? So we come up here. Again, 1 mole, everything here is referenced. So here's carbon. Go in the carbon row, and number of atoms is here. So it's that number. There's 1 mole of carbon for every mole of CO2, and a mole is 6.022 times 10 to the 23rd. But remember, notice, it's not asking you for moles. It's asking you for how many atoms. Okay, so there's that many, 1 mole of carbon in 1 mole of CO2, but there's that many atoms of carbon in 1 mole of CO2. Okay, and then the last question for this set, how many grams of carbon in 1 mole of CO2? So we come back up here, 1 mole, here's carbon, here's grams, so you need 12.01 grams of carbon for 1 mole of CO2. Okay, there are 12.01 grams of carbon in 1 mole of CO2. And that's how you do this. Okay, it's pretty straightforward. Now we'll do a few where it's not always asking for 1 mole. It might be asking for some different number of moles, and all you do is scale it to whatever that number is. So let's just go ahead and do that. Okay, so our next compound is water. So we're kind of familiar with this. So what I'm going to ask you to do is fill out this table. So go ahead and do that. I'm going to do it, and then we will come back and we'll go over. Okay, so take a look at this. I filled out this table. See if it matches what you got. So hydrogen, we need 2 hydrogens for a water molecule and 1 oxygen. And you put those together, that produces 1 water molecule. The atomic mass for hydrogen is 2. You have 2 of them times 1.01 straight off of your periodic table where hydrogen is. Gives you 2.02 atomic mass units. For oxygen, it's 1 times 16 off of the periodic table, gives you 16 atomic mass units. For oxygen, and if you add those together, 2.02 plus 16 gives you 18.02 atomic mass units, is the mass of one water molecule. Now we want to multiply everything over here by this number. And that will give you everything over here in moles. So we take 2, we multiply it by that, we have 2 moles. We take 1, we multiply it by that, we have 1 mole. And we take 1 for water molecules, multiply it by that, we have 1 mole. So these numbers are always going to be the same. And then because this is the special number, the only number that will do this, these numbers, 2.02 and 2.02 are the same, 16 and 16 are the same, 18.02 and 18.02 are the same. The difference is these are in atomic mass units and these are in grams, and that's what we find useful to use when we're measuring in a lab. Now, how many atoms or molecules is this? Well, if it's 2 moles of hydrogen, that's 2 times 6.022 times 10 to the 23rd. If it's 1 mole of oxygen, that's 1 times 6.022 times 10 to the 23rd. And for the water molecules, if you have 1 mole of water molecules, it's 1 times 6.022 times 10 to the 23rd. Okay, so that's how you do the table. Now we can go ahead and answer the questions. So how many water molecules in 1.3 moles of H2O? So in 1 mole of H2O, again, these are the columns we're really interested in. These last 3 columns. So I put a box around them. So everything is referenced to making 1 mole of water. So if we want to know about 1.3 moles of water, we would multiply that by 1.3, and then we'd also multiply this by 1.3. As far as I'm concerned, you don't have to actually do the calculation, just show how the equation would look. So I'll write it like this. Okay, so there are 1.3 times this number, a mole, 6.02 times 10 to the 23rd molecules of water in 1.3 moles of H2O. So if you multiply that out, that would be the actual answer. But as far as I'm concerned, you can just write it like that. I do want you to show the equation. If you want to go ahead and do the calculation, write equals and whatever that number is, that's fine, but you don't have to do that. Okay, how many grams is 5.3 moles of H2O? So 1 mole of H2O is 18.02 grams. So if I want 5.3 grams, that means I have to multiply this by 5.3. So I also have to multiply this by 5.3. Again, it's just, to bake 1 cake, I need this many grams. To bake 5.3 cakes, I need 5.3 times this many grams. Okay, it's just like dealing with a recipe. Okay, so there are 5.3 times 18.02 grams. I'll go ahead and do the calculation just for those of you that are doing it like that. Going to take the time to do it. You ought to know whether you got the right answer. So that's 95.5. We'll just go to 3 digits there. And again, its unit of measure is grams, and then in parentheses the substance, grams H2O. In 5.3 moles of H2O. Okay, so that's the answer there. How many moles of oxygen in 0.73 moles of H2O? So for every 1 mole of H2O, I have 1 mole of oxygen. That's called a 1-to-1 relationship. So whatever the number of moles of water is, I'm going to have that same number of moles of oxygen. In other words, if I multiply 1 by 0.73, because that's what I want, 0.73 moles of H2O, then I'm going to multiply this by 0.73. So, all right, and there's the answer. There's 0.73 moles of oxygen in 0.73 moles of H2O. It's the same number. Whatever the number of moles of H2O is, it's the same number of moles of oxygen. Okay, how many grams of oxygen in 0.002 moles of H2O? So in 1 mole of H2O, there's 16 grams of oxygen. So if I want 0.002 moles of H2O, I need 0.002 times 16 grams of oxygen. Again, just scaling everything down. Okay, there's 0.002 times 16 grams, which equals 0.032 grams of oxygen in 0.002 moles of H2O. So again, be sure you understand that. For 1 mole of water, you need 16 grams of oxygen. For 0.002 moles of water, then you need to take that and multiply it by 0.002, and that will tell you how many grams of oxygen in 0.002 moles. Okay, next up, how many hydrogen atoms in 7.31 moles of water? So in 1 mole, there's 2 moles of hydrogen, which means there's 2 times a mole, 6.022 times 10 to the 23rd. If I want 7.31 moles, I'm going to have to multiply this by 7.31, so I'm going to have to multiply this entire thing by 7.31. Okay, so let me say that again. There's 2 moles of hydrogen, or 2 times 6.02 times 10 to the 23rd atoms in 1 mole of H2O. If I want 7.31 moles of H2O, then I'm going to need to take this entire number and multiply it by 7.31. So let's go ahead and do that. Okay, so there's 7.31 times 2 moles. That's 2 times 6.022 times 10 to the 23rd molecules of hydrogen in 7.31 moles of H2O. So again, let's do that one more time. For 1 mole of H2O, I need this many atoms of hydrogen, 2 times this. If I want 7.31 times this, I need to take this entire term, including the 2, and multiply that by 7.31. And so that's what we did down here. Okay, finally, for this question is how many grams of hydrogen in 0.31 moles of water? So in 1 mole of water, there's 2.02 grams of hydrogen. For 1 mole, you need 2.20 grams. So if you want 0.31 moles of water, then you want 0.31 times that number of grams. Okay, so there are 0.31 times 2.02 grams of hydrogen, which equals 0.63 grams of hydrogen in 0.31 moles of H2O. So the simple thing you do in all of these is whatever you have to multiply that by to get what the question's asking for, you multiply the other thing that it's asking about by that same number. And that's how you do these. Okay, I'm going to break this into 2 tapes. This one's almost 40 minutes. So the second tape will be coming up shortly, and I'll put that up as soon as it's done. Okay, so I'll see you on the next video, and we'll finish up this assignment.